Good morning, everyone. My name is Zachary Zezius. I'm here with the rest of my team, Amy Drake, Charles Humphreys, and Henger Alcantara. We are here representing General Dynamics Electric Boat, and today I'm going to introduce you to our project, the Digital Twin. To start things off, I'd like to thank our technical directors from Electric Boat, Jefferson Wright and Denny Moore. Their guidance and sponsorship of this project has been instrumental in making this all happen. I'd also like to thank our consulting technical directors, Dr. Yan Soon and Mr. Jeremy Peacock, who are always available to help point us in the right direction on difficult questions and offer their unique insights on the project. Our team is a 50-50 split between electrical and computer engineering students, with the electrical side concentrating more on the hardware and the computer side focusing more on the software. Myself and Amy are representing the electrical side, and Charles and Henger are representing the computer side. So, let's get started with a quick overview of the concept of a digital twin. A digital twin is a software representation, or model, of a physical component. It models all the essential elements of that component virtually, and can pull real-time sensor data from the hardware through to the software side. From there, the digital twin can use that real-time data to accurately predict the long-term durability and performance of the hardware, so you always have an up-to-date idea of how long your component will last and how well it will perform under present conditions. This general concept of a digital twin can be used with many end goals in mind, but our intended use case is in the field of predictive maintenance. The idea is that rather than periodically swap out components long before they could fail, or instead of waiting for a component to fail outright, you can always have a clear component lifespan available to you, so you can schedule maintenance exactly when it needs to happen, minimizing downtime and reducing costs. Our general approach for modeling our digital twin was to take a hardware component, in our case a durable pool pump, Hayward's power flow matrix, install an array of sensors on it, and run it to the point of failure under various conditions to build a database of the pump's performance. Then, we would use machine learning and other analytical tools to turn that data into a model that we can use to predict pump lifespan under its current conditions. This is a high-level block diagram of our setup. We have the pump itself at the top, which feeds data through the sensor array to the Raspberry Pi. That Pi then sends that data off to both our live data analysis tools and to a database so that the information can be further analyzed and visualized by the end user. Now I'm going to pass you over to Amy Drake to talk a bit more about the hardware side of things.
Thank you, Zach. This is our project setup that is currently in my garage. We have the Hayward Power Flow Matrix water pump, the 55-gallon water drum, the PVC piping, and a monitor. Choosing the sensors for our project. We first chose our sensors based off of observations of the water pump and how it ran. One of the first observations we made was that while turning it on, the PVC piping moved, so we decided to attach 2 accelerometers to the top of each PVC pipe. We also noticed that running it for a long time meant that the motor on the inside would get warm, so we decided to have a temperature and humidity sensor. One of our major tests we were going to run is the restriction of water flow for the pump, which means the water flow sensor would be most handy in that case for predicting future failure. We also decided to add a waterproof temperature probe because when we met with Troy from Hayward, we discussed the temperature of the water and how with running some certain tests that could change, so we decided to add a temperature probe. As talked about previously in the last slide, we have 2 accelerometers that are located on the top of each PVC pipe, one for the output and one for the input of the water to the pump. We have one temperature and humidity sensor, which is inside the Hayward Power Flow Matrix water pump. We have a water flow sensor, and we have a waterproof temperature probe, which is located in the water. It was fed down the same hole that the left PVC pipe was fed into. To install the sensors, we first put them on a breadboard and wired them to a Raspberry Pi to make sure that we could program them correctly to give us accurate readings. The programming for the accelerometer was a little tricky, but we eventually got it so that it would be reading both sensors at the same time. We then connected all of the sensors in one program to the database to store our data, and while doing that, we were checking the database to make sure that the data was coming in and that the data was accurate. So for the accelerometer, we would kind of shake each one in our hand to make sure it was labeled as the right one in the database. Over the course of a year, our capstone project has had many difficulties. We had an item delay, which was the delay of the water pump. We had to wait about 3 weeks, I would say, for the water pump to arrive, and during this time, our project couldn't really go anywhere. We had all of the sensors working, and we were kind of waiting to get the water pump in to hook everything up. So we couldn't really do much during this time, so we all were researching about machine learning and trying to do as much as we could. Our second difficulty was sensor placement on the water pump. We originally wanted to place sensors on the inside of the pump. So when we first got the water pump, we took it completely apart. During this process, one of the fans on the inside of the pump actually broke. So we decided that we were not going to attach any sensors on the inside unless they could be placed inside of a hole very easily. We decided this because we planned on having 2 more pumps that were going to be delivered, and we were going to run the same tests on them, so we didn't want to have to open each pump like we did this one and break the fans on the inside. The third difficulty that we ran into was water leakage. We originally had a pool hose connected to the water pump, and over winter break, when we came back, the water that was left inside the hose actually broke the hose, even though we had chairs to hold it up so that it wouldn't have a lot of pressure pulling it down. But this did not work. And when we came back to add a flow sensor to it, it needed to be replaced. So we replaced it with PVC piping. Another challenge we had was the accelerometer sensors. These were very difficult to program. I actually worked on it myself along with the help of Charles, because when I was at my house, which is where the project was located, I discovered that the Raspberry Pi was inaccurately reading one of the accelerometers, but only one of them. So I had to do a lot of research and trial and error to figure out how to get them working. Eventually, I figured it out by myself with some help from online forums. The last difficulty we had was the COVID-19 pandemic. We had to move the entire project setup into my garage, which was a process in itself and took a couple days. The PVC pipe was also already cemented together, so when we were tightening one of the piping to the pump, it actually snapped. So we had to work to get the connector loose, and that put us back a couple of days. While testing, the pump overheated, most likely because we broke a fan earlier, and we had to wait a day so that the pump could cool down and we could start running our tests again. This diagram shows an overview of our project. It displays the water pump and the sensors and how they're connected to the Raspberry Pi, which is then connected to the database, and we also ran live analysis tools on the Raspberry Pi, which Charles will talk about next.
Our software architecture mainly utilizes Python for easy-to-use versatility and a wide range of applications. Since we decided on using Python, we also decided that it would be best to use the Raspberry Pi to handle capturing all sensor data and running the appropriate Python scripts in order to save the data into our Postgres database. Multiple remote connections are allowed onto this database, which is why we decided to use Postgres, which allows for further usage of the data, such as queries, insertions, graphing, analyzing, testing, and saving all the data into CSV files for further backup as a fail-safe mechanism. Next, we will talk about the Raspberry Pi and how it handles data acquisition and data transfer as shown in the block diagram. To show some of the processes, the picture on the left displays the temperature and humidity levels from a DHT11 sensor. We made separate Python scripts for each sensor as they each captured data uniquely. We then tested each script by displaying outputs to the user on screen and then saved all the data into our database. After testing, every script was compiled into a master Python script to decrease the amount of database connections to only one and allow for quicker response time. We decided to take the on-screen data a step further by creating a live data analysis tool. This script is essentially a further update from the master script that we previously mentioned. We manually supervised and analyzed data from the water pump as it ran for hours, realizing patterns within readings over a certain time frame and allowing for the realization of threshold values. The analysis tool will continue to read data from the sensors and display them to the user, alert the user when threshold values are reached, and how exactly these values correlate with the status of the pump, and alert the user if anomaly is detected. For example, if low water flow is detected, or if the temperature reading has reached its peak of 60 degrees Celsius, then the analysis tool would continue to monitor these readings. If the readings halted, it would be appointed as an anomaly. However, if the readings continued, the analysis tool would alert the user of a detected failure. After analyzing the data manually, we then wanted to predict future data values of the water pump automatically. Both of these graphs represent our DHT11 temperature and humidity sensor once again. The graph on the left shows the rolling mean and standard deviation of temperature readings versus time, both in red and black respectively. On the right, the blue line shows the predicted forecast of the temperature reading, while in orange is our actual reading. As you can see, the predicted value is very accurate. However, the dataset that we acquired is quite clearly in disarray. There are large fluctuations in our data that depicts where devices were turned on and off arbitrarily. Unfortunately, this data does not accurately depict that of a working water pump, and the new dataset may prove to be more reliable in the future predictions, especially with multiple sensors running in parallel to determine one output, the remaining lifetime of a device. The dataset that we now have is implemented into our GUI to allow a user to easily navigate and visualize different readings of the water pump and its status. Our colleague Henry Alcantara will speak further on this topic, continuing for the GUI section of our block diagram.
Thank you, Charles. For the front end, after doing research on several frameworks, the team decided to use PyQt due to its flexibility, efficiency, and wide arrays of native platform APIs. The graphical user interface interacts with PostgreSQL and displays animated live data from the database. This is the main window of the graphical user interface. The user has the ability to see each of the current readings of the sensors in real time. As you can see, in the right-hand side of the graphical user interface, we have all the sensors that are currently installed on the system, which are temperature, water flow, humidity, and accelerometer. The blank space on the left-hand side of the graphical user interface is a placeholder for the remaining lifetime of the system. Due to unforeseen circumstances, the team was not able to incorporate machine learning into the project. However, Charles was able to do a prediction model for the sensors. If the user were to click on one of the given sensors, the user can see a graph of the past readings of said sensor. For example, this is what the user would see when clicking the temperature sensor. Here, the units is in Celsius. The y-axis is the temperature, and the x-axis is a sample number of that given reading. This is the view of another sensor. In this example, you can see the water flow sensor view. Just like the temperature sensor, the x-axis is the sample number of that given reading, and the y-axis is the pulses recorded by the sensor. Now, some future tasks and improvements could be analyzing the sensor data using machine learning, which will actually help predicting future maintenance periods, and also adding sensor failure detection. Also, security could be taken into account with this given project. That's why we think that delay and data injection detection could be incorporated. We would like to give special thanks to the following for their continued support during the project.